So at the end of class on Friday, I asked how we get the information because we figured out what kind of information, what measurement level we had, but how do we actually get it? Well, this really comes down to the difference between a population and a sample. A population is everyone or everything in the group we want to know about. Now, sometimes defining the population carefully makes it smaller and smaller and smaller as we go along. If I look at full-time faculty at Seton Hill University, that's only about 100 people. If I look at full-time mathematics faculty at Seton Hill University, that's 3. And if I look at female full-time mathematics faculty at Seton Hill University, that's 1 person. I'm not going to get a big generalization from that, am I? But the population is everybody in the group. If I wanted to know something about all the full-time faculty at Seton Hill, that's one thing. All the math faculty, all of the female math faculty. But if I do that same idea, the University of Pittsburgh, all full-time faculty at the University of Pittsburgh is about 1,000 people. By the way, that's only the main campus down in Oakland. Doesn't include Greensburg or any of the other branch campuses. Only Pitt, Oakland. And so I have a very different way of looking at the data. I'm probably not going to get the ability to ask all 1,000 of them a question. So we often sample. Now, realistically, nowadays, gathering answers from 1,000 people isn't hard. Getting them to all answer the question is a whole nother ballgame, but asking all 1,000 people to answer a question isn't all that difficult. Yet if I ask 1,000 people in Westmoreland County who they voted for in the last presidential election, it's quite possible some of them are going to tell me to go pound salt. They don't want to answer that question at all. Some of them will be proud to answer that question. Some of them will absolutely not want to talk to me. So I have to worry about what sort of completion, what feedback I get. But if I actually do get answers from all of the population, we call that a census. So the difference between a census and a survey is whether or not we can ask everybody, whether or not we're going to get answers back from everybody. The reason we call it the decennial, the every 10-year census of the United States, is that the Constitution says you are required every 10 years to count all persons in the United States. Got to count the whole population. What are the benefits and detriments to one over the other? Page 32. Has a list. If I've got a small population, I can ask everybody. If I've got legal requirements, I can ask everybody. If I've got a full database for my population, then I could just query the database. given the size of a database, that could be a short process or a fast process, depending on how the database is laid out. I can ask a question at Seton Hill, and I can get an answer, not just for every current student, but for every student who has ever attended Seton Hill since the establishment of computer records. So I can tell you how many people have taken this course ever at Seton Hill. That's relatively straightforward because the database of all the students exists. When do I take a sample? We talked about bumpers on Friday. Bumpers are rated based on how fast you can hit them, and they won't destroy what's behind them. So destructive testing means it doesn't make sense to do all the bumpers because you keep testing them until you break them, and you don't want to break every bumper that you're going to put on a car. A population that's effectively infinite. I'm going to keep making cars. I'm going to keep making bumpers for cars over and over and over and over. It's not reasonable to test every bumper. It's also not going to give me a result in a reasonable amount of time. If the tests I'm doing on one object take a full day, and I have 100,000 of them to test, I'm not going to get answers for a number of years. That's not worthwhile, is it? Depends on what the item is. How accurate can I be? The more accurate I need to be, the more people I will need to ask. So if I really, really, really need to be accurate, I'm better off doing a census. But if I have a little bit give on my accuracy, if I'll accept some sort of error, and we'll figure out how to decide what that error should be, then I can take a sample. Cost, sensitive information. Both of these things are outside my control as the sampling, right? But if the object is expensive and I'm going to destroy it in testing, I don't want to do it a lot. And some data is protected by law and therefore cannot be examined in total without substantial privacy blindings happening. I'm not allowed to know things. I'm not a doctor. I don't have all of the appropriate HIPAA clearances. I can't ask about medical information. But I could ask the health services to give me a summary of medical information. They could strip it, and potentially, I get a sample. So there's a trade-off here. Questions? If I asked you to tell me the model year of every student's car, those that own a car, what's the year? For everybody in this class, would you do a census or a sample? Which one? For everybody in this class. Census. There are only 70 sitting in this room, right? 8 if you count me. That's easy enough to do. Nice, small group. I can do a full census. But if I asked for every student at Seton Hill, well, there's 1,400 students in the database. 1,300? It's a little harder to do a census, isn't it? I might be able to do it quickly. If they have a car that they bring to campus, and they got a parking pass, the model year is on the parking pass application. So I might actually be able to get that directly as a census. But student owns a car that they don't bring to campus, then I won't be able to get that information, will I? So would I use a census? Would I use a sample? Depends on how I want to go about getting the information and what trade-off I'm willing to make. Make sense? Okay. So I go and I ask questions, I gather information. And normally, we use a capital letter N talk about our population size and our sample size is little n. So n is the size, the number of things we're talking about. If we're talking about people, how many are in the whole group? How many is in the people I asked? The population has some characteristic. Depending on the type of data we gather, whether it's nominal or ordinal or whether it's quantitative or qualitative, I can ask questions about the whole population. But if I didn't do a census, I don't know the answer. A population have parameters. Things we know about the population or things we want to know about the population. How old are Seton Hill students? It's a legitimate question, right? Now, one would assume that most students on campus are between 18 and 22. You get out of high school, you go to college. But I could ask and find out what the range of ages is on campus. I know some students in the Saturday online bachelor's completion program are in their 50s. I know some students who are here on campus, who are full-time students who are in their 30s. They were in the military before they got out, went through the GI Bill, had been out in the workforce for a couple of years, decided to come back to college. Sure. I could ask, what's the average age? What's the range of ages? I could ask all sorts of information because that's a quantitative thing. It would be discrete numerical data, average age, years. And it would be ratio data. 0 has a meaning, but I don't expect anybody to be at college at 0 years old. But it makes sense. Somebody who's 20 years old is twice as much as someone who's 10. So the ratio idea makes sense there. But I don't know this number. And I don't know how to get at it. What I can do is I can take a sample and calculate a statistic. And I use that statistic to estimate the parameter value. So I could go back and I could say, oh, we have the actual average age of the student. And I went out and I asked 100 students how old they were, or pulled their ages from the student database or something. And I say, this is an estimate, my statistical calculation. So the parameter is an actual value that I might not know. Usually will indicate a parameter with a Greek letter, like mu for mean, pi for proportion. I hate the fact that we use pi for proportion, but it's the letter P in Greek, so we'll use it that way. Or sigma for a spread, standard deviation. And statistics are given Roman letters. So a mean, a proportion, and a spread will have X, P, and S to go with those. But I calculate statistics. I don't calculate parameters. I can figure out a parameter if I do a true census, but I don't always have the chance to do that. Questions? So depending on the type of question you're going to ask, the information you're after, you have a target population in mind. I don't know what it is. So let's pull out of the thin air for the moment an idea. I want to look at the S&P 500. I'll call that my target population. 500 stocks, right? Well, that's a small enough group most of the time that I could get a census. So if I asked about the average price earnings ratio for every stock in the S&P 500, am I doing a parameter or a statistic? Aha, I said the target population was the S&P 500. I asked for the average across the entire population. That's a parameter. But if I ask for the number of energy stocks, energy related stocks in my S&P 500 portfolio, is that a parameter or a statistic? I heard mumbling. A statistic. My portfolio is not the entire S&P 500. It takes some of them from it. So I've made a sample right there, my portfolio. And then I used that group and said, what's the proportion of energy related stocks in that? I could then ask, is that representative of the entire S&P 500 or not? If I asked for the proportion of stocks that had a negative earnings ratio last year out of the entire S&P 500, again, that would be a proportion. We're looking at the whole population. So we get to decide when we ask the question, what kind of thing we're after. Then can we actually get it? Once I decide on a target population, I want to create a sampling frame. Now, this is a rarely considered but important piece. If your goal is to figure out something about a population by doing a sample, your sample should reflect the population. Yes? It doesn't make sense for you to ask one group that is skewed in one direction or another without taking into account the population you're looking at. So the sampling frame is who we ask. Now, in terms of reflect the target population, reflect the makeup of the population, this is where we get some problems. They're not huge problems, but they are legitimate problems. We could ask about gender makeup, racial makeup, income. We could ask about geographic location. We could ask about dozens of characteristics of the population. I don't know how many of you have seen this historical photograph from Time magazine. President Harry Truman is holding up a paper. The front page says, Dewey beats Truman. Truman won the election. So why did the paper say it the other way? Because the paper's sampling frame was phone calls. Now, Harry Truman, this is the 30s and the 40s. How common do you think house phones were in the 30s and 40s? Not very. As a matter of fact, my grandfather's apartment building had one phone number for the entire apartment building. Even if each apartment had a phone, you called one, and if somebody was on the line, you got a busy signal. It's called a party line. And so my grandfather, for his entire life, when he went to get my grandmother so that we could talk on the phone, he would say, hold the wire. Which meant I was supposed to keep talking so that if anybody else picked up the party line, they'd know the phone was in use. Because if anybody in any apartment building picked up the phone, it was just like one phone number for the whole building. Everybody could listen in on every conversation. The way the paper went about gathering their information was they made a bunch of phone calls. And since phones were not common, who had phones? And the wealthy skewed Republican and voted for Dewey much more than Democrat voting for Truman. So how do we get our sampling frame? How do we make sure that our sampling frame is reflective of the population? We can do phone lists. We can pull databases. We can get census information from the government. We can get voter registration lists. We can then go through and say, hey, look, the voter registration list for Westmoreland County shows, I'm going to make numbers up, 60% Republican, 30% Democrat, and 10% independent. Our sample should reflect that. If we ask, are you a Republican, a Democrat, or an independent, we better be getting 60, 30, 10 in our sampling frame, or we won't accurately get a picture of what's going to happen in Westmoreland County. A lot of people make a lot of hay of sampling frames. There's a lot of back and forth about this because of the need to accurately count, especially the federal government. Every 10 years, we did it in 2020, we'll do it again in 2030. They count everybody. Or at least they try to. So then it's up to a government group of statisticians to massage the numbers a bit to match what they expected to see in growth and change of population. Again, I'm pulling a number out of thin air, I'm making it up. But if we were to say we expect that 10% of the American population identifies as lesbian, gay, transgender, et cetera, whatever the alphabet group you want to look at, LGBTQIA, et cetera. I don't know all of the abbreviations. Now I should, if I asked a census question about sexuality, if I get 35%, should I think something weird happened? If I get 2%, should I think something weird happened? Like 11%, should I think something weird happened? Somewhere I've got to get some framework to figure out whether or not this is an accurate statistical estimate of the parameter I expect. Maybe I gathered my sample in an unusual way. So let's ask about that. How do we get our samples? There are two main categories by which we gather samples. Random samples versus non-random samples. Again, remember our population size is capital N and our sample size is little n. But let's look at, let's start with random samples. If I want to start with random samples, let's start with the simplest possible method. My population can be labeled. If I were to go through and ask the registrar for all current Seton Hill undergraduate students, it could give me a list of student ID numbers. Yes? Each of you have a 6-digit code on your ID, your student ID number. And then I would have a unique label corresponding to each of you. And I could then pull numbers out of a hat. Yes? Get myself a giant bingo canister and just roll numbers. Yes? My favorite random number generator are shiny math rocks. Lovely little dice with lots of different sides. I can do whatever I want. As a matter of fact, there's even an Excel command. Rand between A, B. If I run this command, it generates a random number from A to B. Now, if I use the numbers from 1 to N, well, then I know what I should be getting, right? But if I was looking at student numbers, they're all 6 digits, so the lowest one is going to be 1, 0, 0, 0, 0, 0. And the highest one, I don't know where we're at the moment. I think we're in the 300s somewhere, 300,000s. But I could randomly pick numbers in that range. So this will generate a random set of integers. If I wanted to do it more than once, I copy and paste however many I need. So those of you that have your computers with you, you should try this and generate, I don't know, 10 random numbers between, let's pull the numbers up there, 1 and 100. If I open Excel, now let me get this right again, open a blank workbook, go back to Zoom, share my Excel book. This is now part of the recording. Good. So let me blow this up so you can see it a little better. Equals rand, and notice what happens. It starts to give me the completion. And right there is random between. And then you'll see in highlighted underneath there, it shows bottom and top. So if I say 1, 100, it generated a random number between 1 and 100. And if I copy and paste this, total of 10 times, there are my random numbers. Pretty straight, right? I do this as often as you want for any interval in the entire thing. However, it didn't happen this time. I'm going to hit paste again. When I hit paste again, it's going to recalculate these numbers. Excel is stupid. It does exactly what I tell it to and nothing else. There's no guarantee that I won't get the same number twice in there. Because each different execution of the command doesn't pay attention to any of the others. Questions about what I did in Excel? Have you seen this before? Oh, good. A couple of you. Here's an interesting point. If I actually did get the bingo machine with, I don't know, 10,000 balls in it, and I started turning and pulling balls out, I can only use each number once. Because once I've got the ball in my hand, it's not still there in the bin to be drawn again. If I ask you to pick a card from a deck of cards, there are 52 options. But once you have that card in your hand, I don't have it in the pile anymore. I can't reuse it. Excel doesn't know what numbers it's already given you because each line is a separate draw from the numbers from 1 to 100. The fact that I had 10 different instances of this command meant it was completely possible that I could get the same number twice. That's with replacement as opposed to without replacement. And when I'm working without replacement or with replacement, it makes a difference to my sampling behavior. The Excel command does allow for repetitions. So it is sampling with replacement. I might not want it to, but that's up to me to catch, not the computer. The computer thinks each command is a separate bin of the numbers from 1 to whatever. This is particularly important in small populations. Because if I only have 100 items and I want 20 or 30 or 40 of them, well, that's a big fraction. And I might actually end up seeing the same one more than once. And the closer the sample size is to the population, the more bias there is in my sampling. Now, at first, this might not be obvious. So let me start with an easy example. I have a deck of cards. Does anyone here not know what a standard deck of cards contains? I said this a couple of years ago, and I had a student who literally had never held a deck of cards in her entire life. A deck of cards is 52 cards. They contain either the numbers 2 to 10, a 1 and a face, J, Q, K, Jack, Queen, King. 13 different values in 4 varieties. 2 sets of red, 2 sets of black, hearts and diamonds are red, spades and clubs are black. So I have 4 of each value. I have 13 within each suit. I ask you to pick a card. There are 52 things you could have picked, right? But you have that card. If I ask you to pick 2 cards, how many options are there for your second draw? I've changed the numbers, right? If I ask you to take 13 cards, by the time you've taken your 10th or 11th or 12th, the number's gotten substantially smaller, right? 1 in 38, 41, 40, 1 in 39. By the time we're down, you've gotten 13 cards. We've got a much smaller pot to pick from, right? In bridge, every player gets 13 cards. Same thing in hearts, right? So all of a sudden, the arrangement and the change that happens, it biases what goes on. We really should only worry if the fraction, population on the bottom, sample on top is close to 1. And we'll define close a little more precisely in chapter 8. Because there's a bunch of, for lack of a better term, complicated looking ugly math that I don't want to get into right now, that really explains why I should be worrying about this. By the way, the other option is also true. What if this number is really small? If little n over big N is smaller than 0.05, or the other way to think of this is if the population is more than 20 times the size of the sample, then we consider our population to be effectively infinite. It means that our chances of hitting the same person or item or observation twice are effectively null. That word effective is important there because there's a lot of, again, complicated looking math that goes into why we would consider such a large population effectively infinite. Some people are not happy with this definition. As I said earlier last week, one of the difficulties in statistics is the trade-off between exactness and achievable. We have to have errors somewhere. This is one of the places where that error is debated. Some people will tell me 0.05 is not a small enough fraction. I need to go to 0.03 or 0.01 or even 0.001. And we'll talk about what it takes to get that effective infinity to be the appropriate size. But if I want to ask about a sample of 50 students here at Seton Hill, well, the population's only 1,200. What's 50 over 1,200? You have a calculator. Don't do this in your head. 50 over 1,200. Use your phone. Those of you with your computers in front of you, your iPads, I guarantee you there's a calculator on there somewhere.
0.041.
It's small enough, right? 041. I can say that's an effectively infinite population compared to my sample. Questions? One of the difficulties in simple random sampling is our definition of randomness. Again, I'm a math geek. There's all sorts of different definitions of random based on different kinds of mathematical definitions. But Excel isn't truly random. The algorithm it uses to generate those numbers in the rand between command is using something called a randomization algorithm. So there's a program in Excel that generates these. That's weird. And it turns out that a lot of random number generators use programs to generate random numbers, as opposed to truly getting something that's random. The Rand Corporation, there's an office in downtown Pittsburgh, put out one of the very first tables of random numbers. Now that sounds like it's a stupid idea if I ever heard one. Here's a list of 10,000 numbers, single digit numbers in a random order. But if everybody starts with line 1, number 1, then everybody knows exactly what you're using. So it makes things predictable, and it made code breaking with random controls not random at all. One of the former employees here, Dr. Jeff Atkinson, left Seton Hill in 2011 and went to work for Konami Gaming Incorporated, designing slot machine algorithms for randomness. And then he went on to work for Management Services Associates in Pittsburgh, where he now talks about where in the casino you place a given slot machine to get the best return on its investment. He's not allowed to play any of them because he knows the insides and therefore he's not allowed to use them, but he does the analysis and it's based on the randomness of the algorithm. So in spite of our idea of using a random sample, getting something to be truly random is hard. There are a number of interesting results about doing things with computers and atmospheric noise and solar radiation. And there's a bunch of interesting results about doing things with temperature. Has anyone here read The Hitchhiker's Guide to the Galaxy? Seen the TV show or the movie? It is a very, very weird book. Their random number generator is a temperature sensor and a hot cup of tea. Why not? So if we can't do random sampling, let's talk about non-random sampling. Or something halfway between. Systematic sampling. I go in to the Bic lighter factory. I need to test lighters for several different things. I need to test them to make sure they light. I need to test them to make sure they hold the amount of fluid that they say we're going to hold. I need to test them to make sure that they burn for as long as we're going to say they burn. I need to test them for temperature, for the cleanliness, for the exhaust fumes, all that sort of stuff. How many lighters do you think Bic makes? A lot, right? So how do I pick which one to sample? Well, I could say, okay, let's take every 1,000th lighter or every 10,000th lighter off the line, and we'll use that. I have no way of knowing what's happened. It's not like they're going to make 9,999 good ones and then one cup. Or the other way around, 9,999 bad ones and then one perfect lighter. Just pick one. But I can say take every 10,000. In a general systematic, I just pick something. This is most useful in effectively infinite populations because I'm going to do whatever test on the bumper. I've picked the 12,000th bumper off the line because we make 100,000, 1 million bumpers a year. I pick every however many. Now, again, ideally, I know n, both the little one and the big one. So I know how many samples I want out of how many people I've got. And then I can just say, oh, well, if that's the case, K is capital N over little n. Now, this could be problematic if there's some regular variation, some periodic behavior. If I was doing something, I wanted to take samples over the course of a year, I'd have to worry about the seasons, wouldn't I? If I'm looking at plant life, well, I'm not going to get much growth right there right now, am I? Ground's solid brick. Forget it. So I need to be careful about this. And again, this could cause a bias. Like spending habits. When do people spend the most money? Not always. Any other ideas? whatever the first day of payday is. Which means most of the spending in this country happens on a Friday or a Saturday. Those are the two most expensive days in this country because paydays are Friday and Saturday. If you're paid monthly, well, that's the first 2 days of the month, right? First 2 or 3 days. Everybody goes, all right, I got to pay all the bills. Thank you very much. If you're paid every other week, it's the 1st and the 15th. And we can chart spending habits against pay frequency. Absolutely. But if I wanted to know when are people doing all this spending, just looking at the days of the week is going to be biased because of that regular behavior. Again, this is something to take into account as we design our sampling. So, what can I do to get around this idea that there might be some variation in my system? The word stratified has its root in the word strata. Anybody know what strata means? S-T-R-A-T-A. There's an Italian dessert called a strata. No? Layer. In our case, I want to think of stratified as having layers to it. If my population has clearly defined subgroups, that's our strata, then I can take a random sample in each layer. Remember, we were talking about voting in Westmoreland County, and I made up numbers and I said 60, 30, 10. Well, then I could say, all right, I want to make sure that I get 100 people. I need 60 from this group, 30 from this group, and 10 from this group to match the proportions of my layers. So let's suppose my population is made up of L groups. Well, then I could say, okay, I'm going to take a sample from each subgroup. Now, that's one way to do it. Another way to do it is to say, I'm just going to take a random sample and then I'll weight the results based on the size of each subgroup. So I could say Republicans make up 60% of the people in my made up version of Westmoreland County. So I will apply a weight of 0.6, 60 out of 100, to the Republican side of my answers. I said that the Democrats made up 30% in my made up version. I can apply a 0.3 weight to that group. There's an example in the text on page 37. I want 200 samples so I can talk about vaccination rates for measles, mumps, and rubella. And the group I'm looking at is 45% female and 55% male. So I could make sure that I get, out of 200 people, 110 men and 90 women, or I could do a completely random sample multiply by 0.45 for the female population and 0.55 for the male population. Stratified sampling happens best when we think about it in terms of locations. We'll talk about that on Wednesday. I hope you all have a wonderful rest of your day, and I will see you then. I should finish chapter 2 on Wednesday. If that's correct, then our homework for that chapter will be due the following Monday, a week from today. You should be able to start a number of these problems. So feel free to come to my office hours and ask me any questions you've got. I will see you all on Wednesday.